Hey everybody, welcome back to chemistry. So in this presentation, what we're going to be doing is considering the rates of chemical reactions. A word that describes looking at rates of chemical reaction is the word kinetics. And so we're going to be looking at the kinetics of chemical reactions. But really, what it comes down to is trying to understand why is it some chemical reactions occur very quickly or are fast reactions, and why is it other chemical reactions occur very slowly or are slow reactions. So if I can increase the slide. So the study of the speed of reactions is called kinetics. First, what I want to do is I want to look at an example of a fast reaction. So what a fast reaction might be is when you put in reactants together, they immediately react to produce products. As I'm going to show you in just a second, we have here two reactions that occur quickly. So let me point out what they are. One reaction here is you drop sodium metal into water and they will react immediately and produce sodium hydroxide and hydrogen gas. But also they are producing a lot of energy, and so this is an exothermic reaction. So another reaction that's fast is a very similar reaction where you drop the metal potassium into water. Now, potassium is, you might recall, the element that is right underneath sodium in the periodic table. So it's in group 1, it's an alkali metal, just like sodium. And it will also react with water. And when it does, it produces potassium hydroxide and hydrogen gas. And so what I want to do is show you a video of this guy named Niall Red dropping these metals into water. Let's see what happens, and hopefully you can understand why these are considered fast reactions. So I'll be with you in just a second as we go to this site. Okay, I'm about to start the video, and so what we're looking at right now is Niall Red is holding a piece of potassium metal. So notice it doesn't look like a white powder, like a salt. Instead, it looks like a shiny metal, and it's because here the potassium is in neutral form. Its atomic number is 19, so the sample of potassium has potassium atoms which have 19 protons and 19 electrons. And so let's see what happens when you drop potassium metal into water. Here we go. So he's got the potassium metal, he's just kind of looking at it. And so now he's going to drop into the water. And what you could see is that as soon as it hit the water, it reacted immediately with it. So this is a fast reaction because as soon as you mix the reactants of potassium and water together, you immediately get the reaction going to produce products. And so the two products being produced are potassium hydroxide, which is dissolved in that water there, but also you're producing hydrogen gas. And so the reason why you're seeing all that flame is because what is happening is as the potassium is generating this hydrogen gas, the hydrogen gas is mixing with the oxygen gas in the atmosphere. There's enough heat generated by this reaction that it will ignite the oxygen and hydrogen, and then they'll react themselves and produce water vapor. But when they do, it's an extremely explosive reaction, reduces a lot of heat and light. So that is potassium. So you can see that this is clearly a fast reaction. So next up is sodium. So he's going to bring up sodium in just a second. So here is a chunk of sodium metal. So you'll notice this doesn't look like anything like the sodium, say, you see in sodium chloride. And the reason is this: when you're thinking about sodium chloride, the sodium in sodium chloride is going to be a sodium ion, and sodium ion has 11 protons and 10 electrons. And so when it's bound to chloride, it is in the form of table salt, and then when you drop that in the water, needless to say, nothing happens. But here we have a chunk of neutral sodium metal. All the atoms here are not ions, they're all neutral atoms, and therefore all the neutral atoms of sodium have 11 protons, 11 electrons. And when that happens, then the sodium appears as a metal. So you can tell it's a metal because it's kind of shiny there. And so he's looking at this way. He's going to drop into water in just a second. So let's see if we can figure out if this is a fast reaction with water. Here we go. And clearly it is. And so the sodium hit the water, and then and it was immediately reacting because you could see the sodium metal sizzling in the water, generating hydrogen gas. And then when enough hydrogen gas developed, it reacted with the oxygen in the air and exploded. So needless to say, don't do this at home. Okay, so we're going to go back to the presentation. I'll be with you in just a second. So if you're curious as to where I found this video, I have this link here. Okay, so that is a couple of fast reactions, and now let us consider a slow reaction. A good example of a slow reaction is a diamond, which is pure carbon, a diamond reacting with the oxygen in the air to produce carbon dioxide. Now, remarkably, this reaction occurs when you have diamonds. They will very, very slowly react with oxygen in the air to produce carbon dioxide, and believe it or not, when they form the product, a bit of energy is released. So this is also an exothermic reaction. And you might be wondering, well, if this reaction is occurring, why have I never seen it? And the reason why you've never seen it is because the reaction is going so darn slow that for any diamond of any size, even if it's a tiny one, it's going to take a million years for that carbon in that diamond to completely react with oxygen in the air to vaporize all that carbon to carbon dioxide. And so that's why you never see the reaction. So the reaction is occurring, but it's going on extremely slowly. So that raises this question: why are some reactions fast and others are slow? And so we are going to try to answer that question. But before we do, we really need to understand exactly how reactions occur when we look at them at the level of the molecule. So to do that, what we're going to do is we're going to imagine a very simple reaction to help us understand this. And so what we're going to be doing is looking at this reaction where the reactants are a molecule which have two different atoms or two different elements bound together, A and B, and it's reacting with this atom or different element C. Those are the reactants, and so they will react. And so look what happens. What will happen is you'll get these products here. One of the products is the molecule B bound to C, and then now you have A as an atom that is released in the reaction. The way this reaction must occur is you can sort of imagine what has to happen is that the C atom is moving in space, and it's going to strike here the AB molecule. And so we say for this reaction to occur that the reactant C must collide with the reactant molecule AB, but then something else needs to happen after that. Once C strikes molecule AB, and it hopefully will strike near B, something is going to happen. One thing that's going to happen is that when C strikes B, you see this bond here between A and B? That bond will need to break. But at the same time, as C is colliding with B, it's going to have to form a bond with B. And so here the bond forms between B and C. So that is essentially how you get this reaction to go, is the atom C must collide with molecule AB, and two things happen. The bond between A and B must break, releasing the A atom, and then C must bond to B, and you'll get the other product. That is sort of a look at this reaction at the level of the molecule, but there's another thing I need to point out. You need to know that there's sort of a halfway point for this reaction, and you need to know what the structure is of the molecule at its halfway point. And so the halfway point looks like this. You have B here in the center, and then what has happened is C has struck B, and you can see as C is striking B, it is kind of halfway to forming a bond with B, but at the same time, as C is striking B, it's pushing off A, and so the bond between B and A is halfway broken. And so this middle point in the reaction has a particular name. It is called a transition state. So the transition state occurs about halfway through the reaction. So here I just state that the transition state is what the molecule looks like at the halfway point between reactants and products. So what is needed for a reaction to occur? So I kind of point out here again, for the reactants to become products, we need C to collide with molecule AB, which will allow C to replace A to form molecule BC as a product, and A will go flying off. The collision between C and AB must be a productive one in order to get this transition state here, or in other words, this molecule that you find halfway. So the question is, how do we go about getting a productive collision so we can get this transition state forming? Well, there are two things that you need in this collision. One thing you need is the correct orientation of the reactant molecules, and another thing you need is that the reactant molecules, which again are A and B here and C, those reactants must have enough kinetic energy such that the reaction can move forward through the transition state. So I'm going to talk about these one at a time. So first, let's talk about the requirement that when molecules collide, the reactants must have the correct orientation to one another. And so here, well, our goal is to react atom C with the molecule AB to get this halfway point, this transition state. So let's look at this picture here that I have now, where we're seeing C here approach AB. And so we might ask, is C at the right orientation such that it can bond to AB and you get that transition state? And so if you actually look at the transition state, what you can see is C is forming a bond on B on the opposite side where the bond to A is breaking. So as you can imagine, if C is striking A from this direction here, this is probably not going to do much of anything. So you don't want this to happen. What you want to happen is C to strike B on the opposite side of A. And so that can probably lead to the transition state. And so really what you need is this situation here. This situation is where C is again striking B from the opposite side of A, and then that you can see will lead to this intermediate transition state. So we really don't want the improper orientation here. That's not going to work. We need the proper orientation of the atoms and molecules in this reaction for this reaction to go to make the transition state. So as you might imagine, only a small fraction of collisions that are in the correct orientation will break the AB bond. So in just a moment, I'm going to talk about why is it we need to be concerned about the kinetic energy of the reactant molecules for this reaction to go. But before I do, I need to remind you about energy diagrams. And so what we have done here is we have this nice energy diagram drawn for this reaction. Here are the reactants molecules, so you have the AB molecule and C, and then here are the products. We have the BC molecule and A. And here, what you can sort of see is that the products have lower potential energy than the reactants, and so that suggests that the products have a lower enthalpy than reactants. If that is the case, then the change of enthalpy for this reaction will be negative, and this is an exothermic reaction. But here's the thing, what we really need to pay attention to now is not so much the change of enthalpy in the reaction. We really don't want to worry about delta H here. This has been pretty good to think about earlier, but right now we're not going to be so much focused on that. So what I want to do is I want to travel forward on the reaction coordinate and follow the energy of these molecules as they go from reactants to products. And so as we saw before, what happens is the energy of the reactants increases until here you get to the transition state, and then it declines, and in this case, the energy goes lower to form products. So now what we can do is we can add sort of a new idea. Here we talked about the peak of this curve, and now you know that here, this is where the transition state is found. The transition state where you have a bond breaking between A and B and another bond forming between B and C, this occurs at the highest part of this curve. It occurs at the top of the hump. And so just to note, you should be reminded what the activation energy of a reaction is. The activation energy is the energy required of the reactants here to get over this hump and to become products. And so I think what you can see is that reactants will need some energy to get over this hump and become products. So this just points out that the abbreviation for the activation energy is EA. So now let's talk about why is it kinetic energy is important to consider with reactants. And the reason is pretty simple. Here you can imagine here that these reactants here, the molecule A, B, and the atom C, have some level of energy. But in fact, this is not the best representation of the value of energy they have. In fact, the reactants, some of them will have high amounts of energy, some will have sort of a middle amount of energy, and some will have relatively low amounts of energy. And so what will happen is that if you have this population of reactants with all these different kinds of energies, the ones with the relatively high amounts of energy will have enough energy to pass through this transition state and to become products. And so one way you might get more molecules to pass through that transition state if somehow you can increase their kinetic energy. If you can increase how fast these molecules are traveling, the amount of energy that they have, then what will happen is you're more likely to have a collision such that it will have the requisite energy to get over this hump. So a question to ask at this point is, how can we make a reaction go faster? So there are two things that you can do. So the first thing you can do is, as you might imagine, if you can in some fashion increase the concentration of the reactants or they're carrying out the reaction, then you will make the reaction go faster. And the reason is pretty easy to understand. If you're increasing the concentration of the reactants, what that means is that there are a lot more reactants for the volume they're in. Therefore, the reactants are closer to one another, and therefore they are more likely to collide with one another. And so if you have more collisions per second, there's more chance of some kind of reaction that will get you through over the transition state into products. But the other way of increasing the rate of reaction, making it go faster, is increasing the temperature. And so if you increase the temperature, what that does, it's going to increase the kinetic energy of the reactants. So right now, the average kinetic energy of these molecules is here, but if you increase the temperature of the reaction, they will have more kinetic energy, and so really their energy will go higher now. And if it's higher, then you're going to have more of a chance that you'll have reactants going over this activation energy hump and becoming products. So here I'm going to show you a really nice demonstration of how increased temperature makes a reaction go faster. So you might remember that diamond will slowly react with oxygen in the air to produce carbon dioxide, but the reaction is so slow that you will never see this really occur to any significant degree in your lifetime or over millions of years. But there is a way we can make this reaction go faster, and Nile Red nicely demonstrates this. All you have to do is stick the diamond, say, in a device that you can heat up, and then maybe you can have a stream of oxygen pass over the diamonds in this very hot environment, and you can just make this reaction go much faster. So let me bring up this video and I'll be with you in just a second. Okay, so what Nile Red has here is a bunch of diamonds. It looks like it's on like a black piece of paper, but he's going to stick them in a glass tube in a minute along with some kind of device that allows oxygen to stream over the diamonds. And then he's going to seal the glass tube and then heat up the glass tube with a blowtorch. And so we'll see what happens. But here he's just showing all these nice diamonds here. Okay. So here are the diamonds, and you can see that they're very tiny, and they're in this glass tube. And so again, he's streaming oxygen across over the diamonds. And so notice he's adding a lot of heat to the diamonds. The diamonds are getting so hot, they're starting to glow. And again, this points out that oxygen gas is passing over the diamonds. And so the remarkable thing is if you get them hot enough and if you wait enough time, what will happen is the diamonds will completely vaporize. And you know what is going on is the carbon in the diamonds is reacting with oxygen to produce carbon dioxide. And so the diamonds have been completely vaporized to carbon dioxide gas. So very importantly, there's sort of a fact that I want you to remember, which could be helpful for you to apply in the future. So I have that here in important to remember. The rate of a reaction typically doubles for every 10 degrees Celsius you go up in temperature. So an example of this is, let's say you have some dirt on some white t-shirts and you want to get rid of it. You decide you're going to wash these white t-shirts with the dirt with some bleach. And so you have a choice. You can do this in cold water or do this in warm water. What would be the best thing to do? Well, the best thing to do would be to do this in warm water, is because not only in warm water will the soap in your wash be able to dissolve better into the dirt, but the bleach will be able to react much more quickly with the dirt to bleach it, and so that it becomes invisible. So in this slide, what I want to do is go back to the first question. Why do some reactions go fast and some go slow? It's because fast reactions have a lower energy hump or a lower activation energy, while slow reactions have a higher energy hump and have a higher activation energy. And so what I'm going to do now is I'm going to put some pictures of energy diagrams on the screen, and we're going to test our knowledge and see if we can identify which energy diagram belongs to which reaction we have considering. So hold on just a second. So if I can reduce the slide. Okay, so what I want to do is I want to take the two reactions we were looking at. One was a fast reaction, one was a slow reaction, and see if we can identify which of these graphs applies to these reactions. And so first, let me just kind of point out the two reactions here. The first one is sodium reacting with water to produce sodium hydroxide and hydrogen gas, and this is a fast reaction. And then the slow one is carbon in the form of diamond reacting with oxygen in the air to produce carbon dioxide. So we're going to try again to figure out which of these four graphs applies to either of these reactions. So let me just kind of give you sort of an idea of what one of the graphs looks like. So here on the x-axis, we have the reaction coordinate, which is basically the time axis of following the reaction from reactants to products. And then on the y-axis, we have the level of energy of the molecules in the reaction. So in this particular graph, there are a couple of things to notice. We have reactants on the left, we have products on the right, and then here is the actual level of energy of the reactants going to products. And I've mapped out a couple of things. One thing I've mapped out is the change of enthalpy of the reaction. And so the change of enthalpy is merely the enthalpy difference between the products and the reactants. But another thing I've mapped out is the activation energy of this reaction. In other words, how much energy must the reactants have to get over this energy hump? And so you will recall here at the top of the hump is the transition state, which I'm abbreviating T.S. And so you'll have to remember that the transition state is where the reactant molecules are kind of halfway in appearance to product molecules. Now you'll notice that all the graphs look a little bit different, so let me point out some things to you. Here in graph B, it's a little bit different. You can see here now the products have more energy than the reactants. There is some activation energy here, but maybe about the same as that, for example. Here in graph C, the products have less potential energy than the reactants. They have less enthalpy than the reactants, but the activation energy is small. And then D, what we can see is in this particular reaction, the products have more energy, more enthalpy than the reactants, and there's a great deal of activation energy. So we can actually make this a little bit of an easier problem by remembering a crucial fact. So you might remember that for the first reaction, which was the fast reaction, and the second reaction, which is a slow reaction, both were exothermic reactions. In other words, when they occurred, they released energy into the environment. Now, let me ask you this question. you see graph B, is this an example of an exothermic reaction? No, graph B is an example of an endothermic reaction. And we know this is because with an endothermic reaction, the products have more enthalpy than the reactants. And so we can also indicate that by putting a plus there. Same thing with graph D. With graph D, the products have more energy than the reactants. And so this is also going to be an endothermic reaction, so we can put a plus there. So basically, we now know B and D are not good graphs for these two reactions because those reactions were exothermic reactions. So we're kind of between A and C. Now we need to figure out which of these graphs corresponds to this first fast reaction and which of the graphs corresponds to the second slow reaction. And so the important point is this. You have a fast reaction whenever the activation energy for that reaction is not very high at all. On the other hand, you have a slow reaction when the activation energy is very high. So now you can answer the question. So here, this first reaction is a fast reaction that can only occur when you mix the reactants and there's enough energy in the ambient conditions in the environment such that those reactants can immediately react and give you products. And so that is only possible if you have a reaction with a very low activation energy, so the reactants have no trouble getting over this activation energy to get to the products. So C here is definitely a graph of the fast reaction. Now, what is the graph of the slow reaction? Well, the reaction may be slow is because for the reaction you have a very high activation energy, and that basically the ambient conditions do not give the molecules enough energy to pass over this high activation energy. And so here it looks like graph A applies to this slow reaction. Okay, thank you for listening, and we'll see you next time.